So I'm Elizabeth. I'm going to be talking about cross-language interposition with WebAssembly component composition. I'm going to talk about what that means throughout the presentation. So if you love observability and WebAssembly, this is a good talk for you. I'm going to establish some visual vocabulary first. So programs that are pure, where they don't require interaction with the environment, will look kind of like this, where they offer some piece of functionality. And then other programs may interact with the world, and they have some dependency that has to be satisfied for them to be able to run. This will look similar like this in the presentation. And these units can be combined to build more complex behavior. So main has two dependencies that are satisfied by calc and logger, and it exposes some piece of functionality called run. So everyone in here knows what WebAssembly is, but at a high level, it's a compilation target for a lot of different environments. So many languages can compile to WebAssembly modules and then run on a VM that runs across many environments. And if the module has some dependency that it needs to be satisfied to interact with the world, then the VM facilitates that interaction. So for cross-language, if we have these units of functionality and they run in different languages, how can we satisfy these arrow dependencies? And there are many different mechanisms that we can do. This is a subset of those mechanisms, but they differ a lot architecturally. So for example, we have the CFFI. There's not a lot of guarantees about isolation here. You have to hand roll the way that you do the interaction with C, but you have this local in-process communication. For Wasm modules, you do have the sandboxing guarantee, you have this in-process communication, but you have very low-level types. And so you have to trust the modules to communicate correctly using these low-level types. So you have to agree on the representation between these two languages. So you have this manual glue code that exists. Then you have WebAssembly components, which give you really nice guarantees here, where you have safe in-process communication between languages, and you have application high-level types that flow between these components. And then you have like RPC, like inter-process communication, where you have the safe polyglot communication, but it has to flow across processes where you have this isolation. And so with RPC specifically, you can have high-level types, but you still have to do that inter-process communication overhead. And you also have partial failure there. So if you're trying to communicate with something that doesn't, but maybe it died at some point, you have to handle those semantics in your application code. Yeah, and all of these different properties in the Wasm component row derive from the canonical ABI. So what does this mean? I'm going to give a really high overview of WebAssembly components in case anyone in here is new to them, which a lot of people know, but it's beside the point. Okay, so we have the example of WebAssembly modules. They communicate with Wasm types, as I said before, so we lose the high-level type. So if main is communicating with calc and for some reason sending a string, then you actually see two I32s that are flowing across the boundary. You don't see that there's a string here. And we have to trust the modules to communicate safely across this polyglot context. But with Wasm components, you have the safe polyglot target where the engine itself enforces the safe communication. So you have a lot more trust in how they communicate. And you retain the high-level types as well. So if you see main passing a string to calc, you actually see a string instead of the two I32s, like in a Wasm module. So inside, if you literally look inside the component WAT, you'll see a core WebAssembly module, and that's where all of the actual logic is. And anytime that you cross this component boundary, you have to lift into a type that is the component type. And then anytime you flow back into a core Wasm, you have to lower it again. And I'm going to show visually what this looks like to hopefully demonstrate what this really means. So trying to demystify this component model a little bit. So again, you have a core Wasm inside this component WAT. So what we're trying to do is get this exported log functionality inside our module and lift it into a component level function. So first, you have to instantiate the module here, and this is all just pseudocode to try to make it a little more concise. So we instantiate our module. There are no imports you have to satisfy, so it's just an instantiation. And then you need to be able to reference the exported log function in the component space. So you alias this into a log core var or reference, whatever you want to call it. So now we do this through aliasing. So now you can use this log core in the context of your component. And then you have to lift, and this is a canon lift, which is an intrinsic in the engine itself. So it knows that it needs to do some code gen or some reasoning about how to lift the params here between the core module and the component functions. And it specifies the type information as well at this lift point. And now we have a component level function. So now we can export this to say, I have this exported piece of functionality that some downstream or upstream component can call. So what does the cross-component call on log look like? We need to have the ability to take this log and somehow get it into a core module function. So we import and we lower, and it mirrors the what we did on the other side, where we lifted, now we lower because we're crossing the component to module boundary. And this again says this is what I need in order to satisfy my dependency, and it has types here, so it should share the same type as what the downstream log would be. Lowering again, and now when we instantiate main, we have this import that needs to be satisfied, and so we pass in our core function, log comp or log core. So now we just thread that into the module instance when it gets instantiated. And if you look at your WAT, you're going to see patterns like this all the time. So hopefully this helps contextualize what's actually happening inside the component WAT. So what about the types? In the component level, we see strings flowing. And this is really like an abstract component level string, but really they're all stored within the memory of the core modules themselves. So the lift and lower code gen is owned by the engine itself. So at the module component boundary, we have this ABI representation. So anytime that you are passing a string, you would need to have that in your core module memory, and then it gets lowered into the target core module memory by the engine doing code gen for that. And then the ABI guest language boundary, we have serialization and deserialization glue. So this is generated by the toolchain of the language that's compiling to the component. So Go knows its own representation of a string. It knows how to serialize that into the memory of the core module so that the engine can do the lifting and lowering. And then the downstream target for Rust knows how to deserialize the ABI representation into its own representation of a string. So this glue code gen is what's owned by the language toolchain. So really, the canonical ABI is this narrow waist for safe polyglot and process communication, where the toolchain just has to own this serialization and deserialization code gen. So composition, what does this mean? Going back to what I showed before with this new microphone. With this inter-process communication, it's using cross-process really to have this clean separation of concerns with great safety guarantees for these polyglot contexts, so thinking about microservices. And so it looks kind of like this, where you have this environment where many different units are communicating over some IPC protocol. But remember that WebAssembly can enforce this with in-process communication. So you can have these really nice guarantees, but you don't have to have the overhead of in-process communication, or sorry, inter-process communication, and you remove the problem of partial failure. And insight into program execution is really essential. And so people that are using this IPC architecture have to do instrumentation in terms of like portable mechanisms. So thinking about service meshes, sidecars, eBPF, and this has high complexity, it's notoriously high overhead, and you're having to manage extra infrastructure in your deployment. But if we move into this composition idea, we would be able to do interposition, where we can target the communication, so the exit and entry points of these units that are communicating in process with these kind of like instrumentation layers. And operating in this way, we also have high application level types, which gives you really nice semantic information about what actually is happening and flowing between these upstream and downstream components. And this looks really nice, but there's a lot of difficulty here. I'm going to talk about the different dragons that we have to address in the following slides. So Splicer, enter this. It's a framework that centralizes this effort, and I think it gives a really nice ergonomic way to express your instrumentation and interpose your instrumentation into an arbitrary composition. So the way that you use it is you write your instrumentation against a WIT interface or a Rust trait. It depends on the tier that you use, which I'm going to talk about later. You configure interposition rules in YAML, but there are ideas to upcycle this into a DSL later, which would be really ergonomic as well. And then this is available as a CLI or a Rust crate, depending on whatever your needs are. And a lot of different capabilities can build on top of this. This is the low-level framework capability that enables you to do this. And then you can build things like dev tooling, security, observability, all these different things. And I've already started building out built-ins that are just native to the framework itself. So you can just target an interface and interpose any of this stuff, just native to the framework. But what's interesting is that anytime that you build something here, you're really building something that ports across any language. So the example of a fuzzer, if you have a fuzzer that has this well-typed information about the boundaries of your application that you're testing, then you can just write your fuzzer in this framework and it ports across any language that you want to fuzz that compiles to a component, which is extremely powerful. So how does Splicer handle subcomposition interposition? So if we have these binaries, they're standalone, there's one component per binary, you could use WAC to compose them together. So now it's this opaque binary that you have to pull apart and figure out what the relationships are between these components that are inside this nested component. So you have to do an analysis to do this. And a little plug, the framework that, or not framework, the crate that I use to do this analysis is called Worm. If you're wanting to do component analysis, this would probably be a good option for you. It exposes this as a visitor on a component IR, so it's pretty ergonomic. So when it takes this binary, it transforms it into a directed acyclic graph, and then you can see the signatures, the functions of relationships between these component nodes as the edges. So given these inputs, what can Splicer produce? So the inputs are the application you're wanting to instrument and the tools you're wanting to interpose on whatever edges. This can be crates or components, depending on the tier, like I said before. And then you have the plan. So this is specifying where you're wanting to match in your target graph to interpose these instrumentation units. So Splicer can validate the interposition. So let's say you want to interpose a tool that doesn't satisfy the typing contract of main, then it'll say that it's not satisfiable. You can also visualize. So it'll take the application, show that this is 1, 2 nodes. These are the edges that come in and the relationship between the nodes, and you can highlight what the side effects would be of the plan on this graph, which is really, really helpful if you have complex plans. You can also generate how to produce the interposition. So looking at this application, if it's a really complex graph, you have to take out all of the subcomponents within this application. You have to take these tools and the adapters that may be generated by Splicer and the depending on what you use. I'm going to talk about more of that later. So it has to take all of these components and generate a script that composes all of these back together as the original application plus the interposed components as well. So you can have this reproducible build without having to rerun the Splicer framework again. And of course, you can also just generate the binary. So there are a lot of different capabilities that Splicer will give you. So for matching primitives, how do you express where to interpose your tooling? So given a graph, you want to be able to have these nice matching abilities. And one example is to find the specific node that you specify. So here I'm looking for logger. I'm looking for all of the edges that flow in and out of this unit, and I can match using glob matching on all of the names. So I'm matching on this edge and this edge for this node. And every one of these matching primitives is just a graph analysis. You can also do subgraphs. So you can find a connected subgraph within the entire graph by specifying the nodes of the subgraph and then the direction of the edges that you're wanting to match on to do that interposition. And again, you can use glob matching on the interfaces. But edges can be heterogeneous, right? So what if you want to interpose on all of these interfaces using the same tool? Because these signatures are not equivalent, so this can be really difficult because you would have to somehow splice a component in here that somehow matches this type signature of both of these edges. So given a target interface, the type signature is metaphorically represented with the shape of these interfaces. You can have one option where you specialize the tool that you've written to the interface, which can get kind of out of control depending on the number of interfaces that you're wanting to do. It would also be obnoxious if you're wanting to have this fuzzer, right? Because your fuzzer can go against interface. So this is like actually not doable for the expressiveness that Splicer can handle. So instead, you can write against an adapter. So now you have this single interface or WIT interface that you write against, and then Splicer code gens the adapter that you actually get hooked into. And when the downstream component gets triggered in this specialized tool context, it'll have one extra hop, so it'll hop into the tool and then into the downstream. But with the adapted tool, it'll have two extra hops. So there is a little bit of overhead here. You have to hop into the adapter, the tool, and then in the downstream. And the adapter that gets generated here depends on the tier that's used by the tool. So what are these tiers? For one, you can have a tool that is guaranteed 0 data access, which is really nice if you're wanting to guarantee something about the access of the tool itself. And this is written against a WIT interface. So you can see that the arguments and the results just flow through the adapter and then never get lifted into the tool. And this is a cross-component call here. Then we have the second adapter tier, which is guaranteed read-only data access. You cannot mutate anything about the data. So as the args flow into the adapter, they get lifted into the tool, and same with the results as they fall back through the adapter on the other side. And this is also a WIT interface that you write against, which is pretty ergonomic. And then the third adapter tier, as arguments flow through, they get passed to the tool, which can mutate them however they want to. You can pass the mutated args to B and then do the same thing with the results as they flow back through. It's not good. Yeah, and this gets code gen directly into the adapter. So you'll note that this was a cross-component call, but anything that is written against a Rust trait can just be code gen into the adapter itself. So you're not having to do this cross-component call with the extra overhead. And then there's a fourth adapter tier, and this is nice for virtualization. So it doesn't even code gen the downstream import here. So it's guaranteed to not invoke anything on the downstream B. And you can take the args that were flowing from A and then generate any arbitrary results that you want. So here is the imposed latency of just the glue code. So this is the minimum overhead for this interposition. So with the specialized gray columns, these are, it's literally just splicing a single component in between A and B that does nothing, just to give like the minimum overhead to compare against what the tiers are doing. So this is one extra hop since it's hopping into the downstream where the component is in the middle. And then 3 is also one extra hop because it's code gen directly into the adapter, so you don't have this extra hop on the tool component. And then tier 1 and 2, like I said before, it's against the WIT interface, so you have to hop into the instrumentation from the adapter. And you can see that the specialized and tier 3, because I mean, they're just components that have no functionality to them really, they're very even across the entire suite of benchmarks, which is just different types that are being passed between components. So you have the scalars on up to lists. And then you can see that the overhead of crossing the component boundary one extra time gives you some overhead with tier 1, and then listing the arguments and the results across the boundary also gives you some overhead as well. But there's like an interesting result down here where not having to lift this expensive list of string across the component boundary in extra time because it doesn't have any data access actually winds up being faster for tier 1. So the expensive types to lift across component boundaries is going to be more performant in that case. And then as the list of U8 gets larger, you can also see a similar performance behavior where you have specialized and tier 3 being pretty similar, like they're basically the same line, and then tier 1 and tier 2 being a bit more expensive, where tier 2 is more expensive than tier 1 because it's having to lift across the boundary. So really, you can see that the number of hops drives performance. So how does Splicer handle resources? If you're wanting to instrument counter to see what happens when increment or current or whatever get invoked, you can instrument this as well. And the way that it does this is through wrapping the resource. So if you look at the code that's generated here, it'll dispatch the instrumentation callbacks, and then it'll invoke that function on the wrapped resource. But remember that Splicer can constrain its instrumentation on subgraphs, which means you have to think about the type as it flows between the subgraph and outside of the subgraph. And that's why you have to be able to wrap and unwrap the resource that you've wrapped, where it looks something kind of like this. So if you target the subgraph C, D, and E, you want to be able to instrument the counter resource inside the context of the subgraph. And then as an edge flows out with a counter on the edge, you have to unwrap it so that you don't mess up the typing across the component, or sorry, the subgraph boundary. And then as you flow back in the context of the subgraph, you have to wrap it again. So what's next? I'm wanting to build out more built-ins, so if you have more ideas, let me know and we can chat about it. Another idea is to upcycle the interposition rules into the WAM DSL. So WAM is a way to do module level instrumentation right now, but upcycling the Splicer capability would enable component level instrumentation. And then of course, I want to do more benchmarking against different patterns like sidecars and service meshes as well. Yeah, so thanks for listening.
We do have some time for questions.
I think this is really impressive work. Thank you. I am curious, because I asked this of everyone, but can you give some color on what is happening during that microsecond?
Yes. So on this chart?
Yes, please.
Yeah. So a lot of this is just the overhead of crossing the component boundary. So it's having to like switch component contexts. So I don't know a ton about the internals of the engine. Are you talking about like this specific one? Or do you mean
any microsecond feels like this is like 10,000 instructions, and I wouldn't have expected it to be that much.
Yeah, I wouldn't have either, but I think the engine people could probably give more like internals information on component overhead.
I think it's the Wasm-time engine people, not to put them on the spot, but if you want to, if there's anything to say, defend yourselves.
So if I'm reading this right, basically the passing a scalar argument, this is the far left-hand gray bar, that's kind of saying that's like 600 nanoseconds to go across component boundary.
Mm-hmm.
That is unexpected. That I would not expect. I would expect that to be along the lines of maybe 5 to 10 nanoseconds. So we should look into that.
We should chat about it then, because I was disappointed by this.
Sounds good.
Yeah, sounds good.
questions? Any questions online? Going once? Great. Let's thank Elizabeth again.
Thank you.